Okay, so let's go through one more example. Still the same question about whether the species are going to coexist or whether, well, one of them is going to be extinct. And now notice that in this example 7, so compared to the previous example, the coefficient at xy, this one is smaller as compared to the previous example, right? So in other words, we reduce the sort of the negative influence of y on x, or which means that essentially what we reduced is the competitive power of y, right? So let us see if this is going to lead to a different result. Again, to find equilibrium points with both populations being non-zero, we just solve the system of equations, and since we can cancel by x, right? By x we can cancel, and by y we can cancel if y and x non-zero. So then we get a system of linear equations. Yeah, and there is just one answer, as usually it is the case with linear systems. And now notice here that x is negative, so which means that essentially is not feasible. So we shouldn't even bother about it, right? So essentially it means that there are just two possible. Well, let me plot here on the xy axis. So we are going to have xy axis. Then we are going to have the equilibrium position here, where x is at its carrying capacity and y is 0, versus that there's going to be another equilibrium position here. When y is going to be at its carrying capacity and x is going to be 0. And of course, that there's going to be an equilibrium position at 0. Well, but then now, is it possible that we are in the same situation as in the previous example? That is, the equilibrium that everything converges to depends on the initial population. So is it possible that trajectories are something like in the previous example? So some approach the equilibrium position where x survives, and some approach the equilibrium position where y survives. But then if you plot it, obviously, if just from the picture, if it were the case, then of course there had to be a saddle point somewhere in between this, right? So which is not the case. So what we see from here is that probably it's not going to be the case, and therefore the winner of the interspecific competition is not going to be determined by the initial population. So rather than this, everything is going to converge to x, or probably everything is going to converge to y. So let us see which of the two. All right, so here is the phase portrait, and from the phase portrait we see that all solutions where the initial condition is positive, well, with both positive initial population, they eventually converge to the case where y disappears, y is 0, and x is at its carrying capacity. Now let us see if we can confirm this analytically. All right, so here is the Jacobian matrix. All right, so it's the matrix of partial derivatives of both right-hand sides of the system of differential equations with respect to x and y. And then at the critical point where x is at its carrying capacity and y is 0, we just substitute the specific numbers into it, and here is what we get. So now notice that this is an upper triangular matrix, so which means that numbers along the main diagonal are just the eigenvalues. So we don't really need to analyze anything further, so because we are given the eigenvalues here. So both of them are negative, so which means this is an asymptotically stable node or a nodal sink, right? And then the counterpart where x is at its carrying capacity and x is 0 and y is at its carrying capacity, again is a lower triangular matrix, but still numbers on the main diagonal. Since it is a lower triangular matrix, it means that on the main diagonal we have eigenvalues. So one of them is positive, the other one is negative, so it is a saddle point, so it is unstable. Confirmed. So which means that the species Y is always going to die out in the presence of the species X, right? So if the initial populations are, no matter how small Y is, no matter how large X is, it's just that the competitive power of X is insufficient. Sorry, is too much as compared to competitive power of Y, and therefore X is going to survive in the long run and reach its carrying capacity, while Y is going to disappear. Right. So let us summarize what we've seen. So with competition between two species, typically we have four equilibrium solutions. This is because when you equate the right-hand side to 0, and then if either X or Y is 0, then it means that either both of them are 0 or the other one is at its carrying capacity. So this is how we can get these 3 critical points. Or if neither of them is 0, then when we equate the right side to 0, then we are going to get a system of linear equations by canceling X in the first equation and Y in the second equation. And then a system of linear equation typically has just exactly one answer, exactly one solution. Now, if the competition coefficients alpha 1 and alpha 2 are, well, relatively small, it means that the competition is not very fierce. So then eventually we are going to get a coexistence. So then we are going to get an asymptotically stable equilibrium with both positive populations. Then if one of them is small, the other one is large, then the species that cannot compete, whose competitive power is weak as compared to the competitive power of the other species, is going to just die out. And if both of them are large, then one of them will die out, but which one dies and which one survives, it depends on the initial condition. All right. Now, logically, there could be, of course, the fourth case, that if both species will die out, so that 0,0 becomes a stable equilibrium. So is it possible? Can you try to figure out? So I suggest that you try to solve it and post your solutions online. Yeah. By the way, it is possible to solve analytically. I mean, it's possible to define which of these possibilities, whether it's the first one, the second one, the third one, well, or the fourth one happens by given this notion of alpha 1 and alpha 2 being small or large, a precise meaning. So what it means, so the precise thresholds. It's just that I didn't do it, but it is doable. And if you're interested, you can either do it by yourself, or you can try to Google it. But anyway, it's not so important. So my purpose was to show that when it is a specific system, it is always kind of, you can find the critical point and interpret it in terms of the system of the two species. So this is something like this you are going to have to do for your course project. So you will need to find critical points, and then you need to analyze their stability, and then you need to interpret it in terms of your story or your model. Okay, so here is a little quiz for you.